Hi, welcome back to the part 2 of the low-pass filter simulation in Cadence. So in this video, we will continue the low-pass filter that we did in the previous video. If you haven't watched that one, please watch it, because in that video, I introduced about the basic theory of a low-pass filter and also how to analyze the low-pass filter in AC analysis in Cadence. But in this video, I will demonstrate the transient analysis, or we can say like analysis in the time domain of the low-pass filter. And next we will make the transient analysis much faster with one type of simulation, which is parametrization, and you will know when we start to do the parametrization. And lastly, I will introduce about the bandwidth function, where we can have the expression to automatically measure our -3 dB frequency, or the bandwidth of our low-pass filter. So now let's continue. For the transient analysis, of course, we need to have the analysis for transient. In order to do so, we need to go for the mesh file, and we go to the blue arrow. We click so we can change to another perspective of the mesh file, where we can add another analysis. We double click in add analysis, we choose trend, which is transient, and then we can choose the stop time. So let's say, of course it depends on you what time you want to have the stop time, but in my opinion, I would plan to do 3 tests for the transient. One test is for the signal when the sinusoidal input had the frequency lower than our -3 dB frequency, which is 1 kHz. One signal at the 1 kHz frequency, -3 dB frequency, and one sinusoidal with frequency higher than 1 kHz, and we can start to observe. In that case, we will need to have the stop time be able to accommodate all of the 3 analyses. Otherwise, we will have to add the same transient analysis and just change the stop time, which is very inconvenient, right? So you need to have the slowest stop time in order to accommodate the whole 3 cases. Let's say I choose one signal had the oscillating frequency, or the sinusoidal signal had the frequency at around 100 Hz. So the 100 Hz is the lowest one, the frequency, the slowest frequency. If it's the slowest frequency, then the period will be the biggest period. So one period of 100 Hz is 1 over 100. It will be 0.01 second for one period, the signal with 100 Hz. So maybe I can put the stop time, let's say 3 period of the slowest signal input, so I will have 0.03. And this is for accuracy. By default is error preset, we can just use by default. If you choose the conservative, then the simulation will take a lot of time, but the accuracy of the simulated result will be much better. In our case, we don't need that. We only need to see the principles of the low-pass filter, so that's why we don't choose anything here. Transient noise, we don't care about the noise yet. We just assume everything is perfect. So we click OK. Now we have the transient analysis together with the AC analysis. We can check both of the analysis at the time. So when we run the simulation, we run both of the simulation. If you uncheck the AC analysis, then when we run the simulation, only the transient. So you cannot see the butter plot anymore, but if you check both of them, you can see the results related to both simulations. I prefer having both in this case. And then we go back. Of course, we need to go back to our schematic. Why? Because here, if you go back to the schematic and then you click in the source, you press Q, you can see that we have not set any signal for our V-in source. Now we need to have a signal. And in order to do so, you can see that there's a amplitude, which is the amplitude of our input sinusoidal, and the frequency. We need the frequency. So this is the frequency. In order to easy to observe, of course, let's put it 1 volt. And the frequency, we first test with the frequency lower than the bandwidth frequency. The bandwidth frequency is the minus 3 dB frequency. And in our case, the minus 3 dB frequency is 1 kHz. And I plan to choose the frequency lower than 1 kHz is 100 Hz. So we press OK. Now you can see the parameter appear here. Of course, if you open the property of the V-in source, of course we need to change the AC magnitude to 1 again, so we can have the right magnitude of the transfer function. If you want to know why, I already demonstrated this point in the previous video, so please watch it. If you haven't watched it, you can find the link in the description section of this video. But in this one, we know that in order to obtain the correct transfer function, the correct maximum amplitude of the transfer function, we need to set the AC analysis to be 1 volt. And this amplitude is the amplitude of the input sinusoidal we input into our low pass filter. And the frequency for the sinusoidal is 100 Hz. We press OK. Now let's label the signal so we can easily distinguish what is the input and what is the output. So it's easy for us. We can go to create, we choose Y name, or you can press L. Press L in the keyboard and you type V-in and you put it here, and L again and you type V-out, and this is our V-out. You can check and save. That's good. And we go to our master file. Master file is the simulation file. Of course, this one is added earlier when we have not labeled our wire name. Now let's choose the signal again after we already labeled them. Now we choose the input. Now you can see that the Y name has the label that we just labeled it, and it's very easy to track when you have lots of signal. Here is the circuit is quite simple, so it's really easy to remember. However, it's better to label the Y or the signal properly, so in the simulation we can easily observe them, and we should save them when we run the simulation. Now let's delete what we don't need. You press the signal that you want to delete and you press Ctrl to choose all the signal that you don't want to, and here you can choose delete. And in order to be in that perspective of the master file, remember we should be at the output setup perspective. If we go to the result, it's different. Okay, we can only do the signal manipulation in the output setup tab. So now I think it looks good. We have enough of signal that we need for the transient analysis and even for the AC analysis, because for the AC analysis or to see the transfer function, we already have the V-out signal where we can see it. Everything is good. Again, we can go to the blue arrow to check that we already have enough analysis tests set up here, and yes, we have them all. Now let's go back one more time and we press run the simulation. And then we wait. Okay, I think it's finished. We have no errors. That's a good sign. And let's check our V in signal, which is the sinusoidal with the amplitude of 1 and frequency of 100 Hz, and we plan to see 3 periods according to the transient analysis. So we can right click and we plot, and this is the AC response, mean the Fourier transform of our V in signal. And our V in signal, of course, is always 1. So we don't care about this one. It's not really meaningless, but don't care about this one at this point. We can delete it. Yes. And now, how many periods we can see here? Oh, I don't know. How could it appear here? We can maybe delete it. Yes. We just choose it and then we press the keyboard delete and we can delete it. Let's use the vertical marker. We press V on the board, and here is 1 period for us, which is 10 milliseconds. Right? Yes, 1 period. And if you press another V, we will have the second marker, and we go to 20 milliseconds, which is our second period. And the last one is here, 30 milliseconds. And correct, right? So that's the V input. Now let's plot the transfer function. So maybe we can theoretically predict how the output signal will look like if we have such an input signal. Let's go back to the master file, the results perspective of our master file. Of course, now we need to plot the transfer function. So we choose V-out, right click, and we choose direct plot. We choose AC magnitude and phase. We choose V-out. Pay attention, when I click this way, it doesn't mean that my V-out signal is selected. Let's choose it again. Yes, now it's selected properly. We can run the simulation again. Oh, unfortunately, when I run the simulation, it overlaid the previous one that I want to keep. But let's say I will keep this one, and we can split the trace, and I will do some modification in order to make the look more convenient. And now we have the bottom plot on top, and we have the phase downward. And let's have the vertical marker. We will put at 1 kHz, which is our, what is that? The bandwidth or the -3 dB frequency point. Okay, now let's go back to the master file and plot our input signal in the same one. Go to this window, open master file, and we choose, let's say, new sub window, and we choose V in, right click, and we plot. Now you can see, right, also it plots the AC response of our V in, which we don't want. Earlier, right click and we delete it. Okay, now as we say, this signal has the frequency of 100 Hz, right? If it's 100 Hz, then how can we predict our output? Let's be in the frequency transfer function. We press another vertical marker and we go to 100. 100 will be here, somewhere around here. You can look at the marker. I think this one is close to 100 Hertz, and at 100 Hertz, what is the thing we can see? Oh, it moves. Okay, now it goes back to what we want. Okay, we can see that the output amplitude, the ratio between the output amplitude and the input amplitude in dB will be roughly like minus 48 milli dB, which is really close to 0 dB. So we can say it's 0 dB. So we can somehow approximate that the amplitude of the output will approximately the amplitude of the input. And next, what do we have for the phase shift? If we look at the phase shift, here, which is minus 5 degree, very small. Minus 5 degree is really small, almost like 0 degree. So we can say maybe the output signal will approximately the input signal. That's what our theoretical prediction based on the transfer function. Now let's go back to the transient, and we can plot the output on top of the input in order to compare with our theoretical expectation. Go to activity. Of course, when we choose this sub-window, we need to choose this sub-window, so the program knows that it will have to plot or append the plot of the V-out on top of this window, not the transfer function. So we go back to the mesh draw file. We choose here append, and V-out we choose plot. We can delete the V-out from here, and here this is our V-out. We can change the color to maybe blue, and you can see that the V-out and the V-in exactly the same, almost exactly the same. We cannot distinguish such a small difference in the amplitude and different in phase with our eyes. We need to do measurement automatically, measurement with some automatic function. But of course, this is not our focus. We just want to really understand what's happening when we look into the transfer function of a system. Okay, everything is as prediction. You can turn off maybe like this, and we only see the V-out, right? If we turn this one on, it's exactly the same. Yes, they are on top of each other. You can see they are almost like on top of each other. Even the amplitude, even the phase. If there's a phase difference, you will see the difference between them. You will see they are two separate signals. But now the difference between the phase is so small, and even the difference between the amplitude is so small. So we cannot distinguish them by our eyes. So we can say they are exactly the same and very, very correct according to what we expect when we look at the transfer function. Okay, now we can have another test where we will have the signal, input signal with the frequency maybe higher than 1 kilohertz. Let's say we can choose it to be 10 kilohertz, roughly around here, 10 kilohertz. We go back to our transient. We go back to the schematic because we need to add another signal. We choose our source. We press Q to modify the property of the source, and we want to have 10 kilohertz, so it will be 10 E plus 3, which is 10 kilohertz, and we press OK. 10 kilohertz. Good. Save and check, and then we run the simulation again. Let's keep our old simulation results in those windows so we can compare them together. Okay, and now let's go back to the transient to see whether it's finished. Okay, the simulation has been finished. We can choose another new sub-window, so we can keep the two sub-window. This is one sub-window, and this is another sub-window. and we want to plot the new results that you just simulated in another sub-window. So we choose another sub-window, and we will plot our V in. Plot it. Of course, it's a little bit too big to see. Maybe we can zoom in. Is there any way that we can zoom in? First, we need to delete this one. I need to find out a way to zoom in and zoom out this one. Maybe view, zoom in. Yes. So we can choose the graph and we press zoom in. But in this way, we don't see the two amplitude anymore. Oh, okay. So maybe you can just remember this result. When we have the V in lower than the minus 3 dB frequency, we have V out almost the same with our V in, according to our theoretical expectation from the transfer function. So now I'll delete this one. Yes. So I can see this one, and I can easily zoom in to be like 1, 2 period. Okay, this is our V in. Now let's go to the activity again. Of course, first we need to choose this sub-window, okay? So we can plot the V out on top of it. But let's say we need to have the theoretical prediction before we plot the output in order to understand the transfer characteristic in a more thoroughly way. Okay, I just wanna expand this one. Okay, so we can move this one to, this is our old result where we have the input at 100 Hertz. Now we will add another vertical bar, another vertical marker, and we move to 10 kilohertz, which is here. I'm trying to be, okay, 10 kilohertz. What do we see? We see that the ratio between the output amplitude and the input amplitude will be around like minus 19 dB. Minus 19 dB. If we do the conversion, then it will be around like minus 19. It will be like the V out amplitude over V in amplitude will be approximately equal to 0.1. It means the amplitude of the V out will be 1/10 the amplitude of the V in. So we have V in amplitude around 1 volt. So our V out will be just around like 0.1 volt, roughly somewhere here. And the phase shift can be understood in another perspective, which is there's a delay for our output signal. The output signal doesn't come immediately together with the input signal, but it will come a little bit later, and that later is defined by the phase shift with a minus 84 degree. So it almost like 90-degree phase shift. So you will see there will be the difference. Here, the amplitude of the output will be around here 0.1 volt, and the signal will somehow got shifted according to the peak. The peak of the output signal will be somewhere maybe here, around here. But let's see. That's the prediction from our transfer function analysis. And before that, we need to choose this sub-window so we can plot our output signal on the same window. Now we choose the V out, we choose a pen, and we plot it. Okay, let's delete these trays. We don't need them. I will change to another color. Oh, now you can see, right? You can see as we predict the we can even use the marker here, another vertical marker, and we can turn, because the vertical marker will show all of the value of the points that it crosses. We don't want to see the V in, so we can click in the eye to hide the V in, and we only want to see the V out. We want to see the peak, and the peak is around like 165 millivolt. Yes, it's very close to 0.1 volt that we predict. And you can see the phase shift now. Let's compare them. By seeing the phase shift, you can see that the peak of the output is around here, while the peak of the input is here. So the output is delayed almost like roughly 90 degrees, as we can read from the transfer function. And yes, this is how we can analyze the low-pass filter in the transient analysis. One more test, which is we'll have a signal exactly at the minus 3 dB frequency, and at the minus 3 dB frequency we can see the minus 40 degree shift, and the amplitude of the V out over the V in will be roughly like 0.7. It means the V out will have the amplitude around, I guess, like 0.7 volt. Okay, now let's go to the activity. Oh, we can delete this window. We will delete this one. Yes. We only keep the transfer function. Now let's go to our transient, and we need to modify the input signal. Choose the V in source, and we modify this one to 1 kilohertz. We save and check. We go to the Maestro file, and we run the simulation again. Okay, I think it's complete. Yes, it's complete, and we choose new sub window because I don't want to ruin the transfer function that we already plot. The transfer function wouldn't change when we change the frequency of the input signal, because the AC transient analysis is based on this AC magnitude, not in the amplitude or the frequency of the input sine wave. So let's go to the Maestro file, we choose new sub window, and we choose plot. And this is our signal. Delete this V in and go here. We would choose append. Let's check which sub-window am I in. I should be in this sub-window. And now we'll plot this one. Yeah, yes, this is what we predict to be based on the transfer characteristic. Maybe I would choose another color. Blue again. Okay, let's see the blue signal. We will put a vertical marker, and we will enable the input. We choose the output only, so we can see the amplitude. And the amplitude is 741 millivolt, roughly 700 millivolt as we expect, because minus 3 dB means the ratio of the V out over the V in is 0.7. And if you enable the V in again and you see both of them at the same time, you can see there's a bit shift between the V out and the V in by looking at the peak. So the peak of the V out is later than the peak of the V in a little bit. How much late? We can see that is late by 45 degrees. Yeah, you can see here, minus 45 degrees at 1 kilohertz. If we have the 1 kilohertz sine wave input, the output will be late compared to the inputs, around like 45 degrees, and the amplitude will be just 70% of the amplitude of the V in. So that's what I want to show you about the transient analysis of a low-pass filter. But there's a faster way to do such a test. Instead of doing one signal by one signal, we can use parametrization to simulate 3 cases at the same time. How to do that?